two fundamental theories in physics are those of quantum mechanics and Einstein's theory of general relativity. Quantum mechanics deals with the small scale, describing the motions and interactions that occur on the atomic and subatomic levels. On the other hand, general relativity concerns itself with the large scale, describing motions and interactions that occur between large bodies within something called space-time. However, quantum mechanics and general relativity aren't compatible. They don't fit. So let's talk about why. The first disagreement is gravity. In quantum mechanics, gravity is one of the four fundamental forces that explain the ways particles can interact with each other. In general relativity, gravity is a resulting geometric property of the curvature of spacetime. Think about an object on a trampoline. The object weighs down the trampoline and creates a well towards which other objects are pulled. That's the force of gravity. The second discrepancy is probability. General relativity outlines causal relationships that are deterministic. We know what has happened in the past, and we know what will happen in the future. Quantum mechanics, though, is probabilistic. Future events can only be predicted, not known. On top of that, the Heisenberg uncertainty principle states that you can't precisely measure both the position and momentum of a particle at a given point in time. These aren't even all the differences between the two. They also disagree on the concept of time and whether or not space is cohesive. But each theory is technically right in its respective situation. It's just when you're operating at the large and small scale that the two theories come into direct conflict. And this happens when you have a large amount of mass condensed into a small amount of space. For example, at the center of a black hole, the entire mass of a black hole is condensed into an infinitely small point. At that point, gravity and the curvature of spacetime become infinite, breaking down our laws of physics as we know them. Which is why we need quantum mechanics to step in and try to explain what's happening at the particle level. However, we can't reconcile the two theories. If you drop two plates, you can't take pieces from both and make a new plate. In the same way, you can't take pieces of quantum mechanics and give them to relativity and hope everything works out. The math breaks down. And that's why physicists are looking for what is called a theory of everything, which could explain all physical phenomena without those type of conflicts. And there have been many attempts at doing just that, from string theory to loop quantum gravity, but so far there are shortcomings with all of them. String theory requires 10 dimensions to work and hasn't been proven experimentally, and loop quantum gravity is a stepping stone towards finding a theory of everything, but it doesn't quite check all the boxes. So we're still looking for a theory of everything that would help us understand not only what is happening at the center of a black hole, but also what happened at the very beginning of the Big Bang. Maybe a theory of everything is just what we need. We'll see.